Hello and welcome back to Spring 2024 A2 sessions. This is session 3 with myself, Mr. Black from Pengli School, and I'm going to be going over iodine Clark reaction and discussing order and mechanism with you today. Okay, so let's get into the first slide. So you can see here, I've just picked this up from the practical booklet. So, you know, things that might be worthwhile having you while you're watching this presentation would be your practical book, your data sheet maybe, and also a calculator. Okay, so let's look at this then. The iodine clock reaction, really important. You're looking at the reaction where you're going to look at the kinetics, and you're going to be working at the order of the reaction. And from that, we're going to look a little bit at what we call mechanism as well. So the reaction itself, then you can see here, hydrogen peroxide, you've got iodide ions, so typically be adding some potassium iodide for that, and it's in acidic conditions. Now, I'm just very quickly going to ask you to look at the balanced equation, because it's something that you're asked to do in exams quite a lot, and that's to work out a way you can monitor the rate of this reaction. And if you look here, it's fairly limited. You know, typically I'm going to be looking for a gas being formed, and we can't see any gas being formed here. We'll look at some other methods that we could perhaps use. But one of the things that you'll notice is this iodine, and it's well worth remembering iodine is a coloured substance. Okay, and so what would you expect to happen in this reaction? Well, we'd expect to see iodine start to form. Okay, and seeing the iodine start to form, we'd start to see it go darker in colour. Okay, and as the reaction proceeds, it's increasingly dark. The volume here is increasing, by the way, because as soon as you start this reaction off, it starts producing iodine almost instantly. Okay, as you can see how dark it actually goes. So what's a way we can monitor this reaction then, other than the iodine clock mechanism that we are going to do? And if you look at the bottom of the page here, you can see I've put a little clip there. You can click on that link and follow to the actual video on YouTube where you can see the reaction happen. So hopefully you've recognised that you're going to be using some colorimetry. So how does colorimetry work? Well, if we go back to the colour here, this colour that we see forming, it's not that it's suddenly giving out a different coloured light. So that's not how light works. Hopefully you appreciate that already. What's happening here is that white light shining for our sample, and suddenly our sample starts to absorb particular wavelengths of light. And absorbing this particular wavelength of light results in a colour being then transmitted. And you can see here, what we've got here is actually a colour wheel, and we have kind of like corresponding colours. So, for example, if you absorb a blue-green colour, then you would see a red solution and so on. So the point I'm trying to make here with you then is that our sample's coloured, and therefore it's absorbing a particular wavelength of light, and colorimetry is a technique that allows you to monitor how the transmittance of a wavelength of light changes over time. So you can see here we've got our white light. Okay, what we do is we select a particular wavelength of light that we're going to pass through the sample. Obviously we'll be selecting a wavelength of light that's going to be absorbed by our sample, either by a reactant or product, and then you can see as it passes through the sample, because it's been absorbed, then the detector can tell us how much has been absorbed and allows us to see what the concentration is like. So, for example, if the concentration of the coloured substance as such is increasing, the absorbance is therefore increasing, and therefore we detect a bit less wavelength at the detector. Okay, and typically we'll produce a graph like this. So you can see here, we've got time, and here we've got the absorbance of the particular wavelength. And interestingly, it's just a graph I picked up off the internet. We can see we've actually got 3 sets of results here, okay? And you can see actually the gradients of these curves look very similar. And that would suggest to me, whatever they're changing the concentration of here, each of these lines represents different concentration, doesn't seem to be affecting the rate of this reaction. And we'll come on to this a bit later, but that would suggest to me whatever this reactant is, it's not affecting the rate, as we can tell from the gradients being the same. That would suggest to me whatever their reactant is that are changing is probably a 0 order reactant. So yeah, that's your colorimetry technique. Okay. I've got a quick question here. This is actually from transition metals, but again, hopefully, transition metals are coloured substances, and therefore, if you wanted to monitor the rate at which this equilibrium is achieved, we could use colorimetry again. Okay, and you can see here that it tells you about the species being coloured. Hopefully, you recognise the colours of those species anyway from your topic on transition metals. And you can see here that basically the question is asking us, if you were to monitor this reaction, what wavelength of light would be suitable? Okay. So that's the question there. I don't think I've actually got the question on the page here, run out of space, but it's asking you what wavelength of light would be sensible for monitoring the rate at which this reaction occurs. So I'm going to actually have a quick look at that and have a think for yourselves. Okay, and basically it's a value, and you see here, that's below 600 or above 560. And the reason is what we don't want is to, for example, we won't want something here because both are absorbing light. Okay, so you don't want to cross over. So you want anything that's below 600, sorry, above 600. Okay, where we're not getting absorbance here, and we can have anything below 560, which is, really around this region here. So we don't want a crossover kind of wavelength where the reactant and the products are both absorbing that wavelength of light. Just to prove that one in there for you. Okay, so we're not actually going to be looking at colorimetry today. I just want you to have an awareness of the fact that you could use colorimetry because you're performing iodine. Looking questions as well, if it does mention that there's a coloured species, that's all, colorimetry is the method to use. Okay, so we're going to look at the using a clock reaction method. And what's a clock reaction? Well, a clock reaction is what I call a timed event. Okay, so for example, we can monitor this reaction using a timed event. Obviously, just to point out, there are other ways that we can monitor this reaction. I wonder if you could think of a way you can monitor this reaction yourselves. Well, you might have said weigh it. It's a good idea. You are producing a gas, so we'd see the mass go down, which would correspond to the amount of mass of gas lost. However, you can't do that with hydrogen because the gas is too light, it's got too low a density, so you won't be able to measure that accurately enough. But if you did see a gas being formed, it's a good method to go for there, mass loss. Or of course, you could collect the gas over time. And I think if this was with hydrogen, that's certainly something that I would look at doing. But just to point out as well, you could actually do this as a clock reaction. For example, you could, if the gas was heavy enough, let's say it's just carbon dioxide, bear me a second, sorry, you could kind of say, well, I'm going to measure the time it takes to produce a certain amount of gas, or the mass to go down by a certain amount. Okay. Or likewise with collecting the gas, you could actually say, well, I'm going to time how long it takes to produce a certain amount of gas. Okay, so those would be your methods for a clock reaction on these two reactions here. Just to point out to you saw that pop up earlier, the thing with doing that is you'd obviously have to make sure that the volume of gas you collect corresponds to the steepest part of this curve, because what we don't want to do is say, oh well, we'll see how long it takes to collect I don't know, this volume of gas, and if you look here you can see the rate's actually slowing down by this point. So it'd have to be a relatively small amount of gas or relatively small change in the mass. So yeah, that's a timed event. Okay. The other thing, of course, with this reaction, we could time how long it takes for the zinc to fully dissolve. So like I say, clock reaction is just a timed event. Anything that you can kind of monitor happening and ascribe a time to could be used measured with a clock reaction. Okay. So what about this reaction then? So you should be familiar with this, and hopefully you know how this what would be our timed event here. Just before you do that, just balance the equation up quickly. So I'll give you a moment to pause. Okay, and you should have put 2 in front of the HCl there. So what's our timed event here? Well, hopefully you've looked at the state symbols. That's always a good thing to do. There's nothing that I associate with a colour there particularly, other than the sulfur. But the state symbol's always a good go-to. So you can see there you've got aqueous reactions, reactants forming a solid. So we get a precipitate forming. And hopefully you remember then what we could do to monitor the timed event. So what's our timed event? Well, our timed event is where we have a cross that forms during the reaction. Sorry, not forms during the reaction. We time how long it takes for a cross to form in this reaction and to then obscure the cross. So we time how long it takes for the cross to disappear, and that is our timed event. Okay, obviously, you know, things to talk about fair testing here. We'd have to have the same conical flasks, really. Just simply because you want the same depth of solution. Okay, if you had a wider base in your conical, when you're doing like different temperatures or concentrations, obviously the depth of solution would be more shallow, and therefore you'd be able to, you know, see the cross for longer with a shallower kind of depth. Other things, you know, you'd have to consider things like the concentration of the acid or the concentration of the thio, depends if you change one of them. We'd want to keep the temperature same as well. The cross, of course, would have to stay the same. We want a cross that's kind of more darker than another cross. Obviously, the darker cross would last for longer. And the other thing as well is you'd want the same person measuring the time it takes that cross to disappear, because it involves a judgment. Okay, so that's your clock method there. You can, you know, if you've got a precipitate forming, the clock method's a good one to go for. Okay, so how do you work out the rate once we've timed our event? It's fairly straightforward. It's just literally 1 over time taken. And the unit of rate then with a clock method is obviously s to the -1. If you are measuring in seconds, which usually would be, although it could be min to the -1, hours to the -1, but typically it's going to be s to the -1. Okay, so we're going to go back now to the iodine clock reaction. So there's no precipitate forming here. So that's not something that we're going to be able to measure as a timed event. So what is it that we measure as our timed event in the iodine clock? Okay, well, it's to do with the iodine. Okay, hopefully that you know iodine produces this really strong blue-black colour in the presence of starch. So in the iodine clock reaction, we place a small amount of starch, and what we're timing really is as soon as we see this blue-black colour appear. Okay, and the advice really is as soon as you see it, that is the timed event. Don't wait for it to go kind of this colour, because you've gone way past that point. Okay, so yeah, it's as soon as you notice that blue-black colour appear, that's your timed event. And the thing to point out here about this blue-black colour is that you actually need very, very, very little iodine to be formed for that actually to form that blue-black colour. So we're going to talk about then some of the logistics that we need to kind of use in the iodine clock reaction. And one of those is that we have kind of a second reaction going on at the same time. And this is the reaction between thiosulfate, which is this species here, and the iodine that we form. Okay, and we'll talk about why that's important now. But before we do that, let's look at the half equations, kind of do a bit of crossover. Just very quickly, you should know these half equations. The thiosulfate is obviously a bit more difficult than the iodine one. So again, I'm just going to do a little pause for you where you just kind of do the half equations for me. Okay, so you can see there, that's what we form with the thiosulfate. And then we need to put that in to balance up the thios. So then we've got the 4 sulfurs. And I'm just going to pause again for you to work out how many electrons you need to add in. Okay, and then hopefully you've come up with your 2 electrons there. There are different ways you can work out your oxidation numbers, and use your technique that works for you. Obviously, one of the ways you can do it is you can work out your oxidation states on the sulfur here and here. and you can see you're going from, well, 3 times -2 gives me -6. So this is -8 with a -2 charge here. So each sulfur here must be in the +2 oxidation state. Okay, sorry, +4 oxidation. I'm going to bear with a second. 3 times -2 gives me -6. Okay, and then, oh yes, -6. Okay, and we want to retain that -2 charge. So yeah, we need the sulfurs to come out as +4. That was me rushing there. So 2 sulfurs, each in the +2 oxidation state. And then we come over this side and you can see that we've got 6 oxygens. Okay, so 6 times -2, it comes out as -12. We want to retain a -2 charge, so we need to have a +10 here. Okay, and then we're going to divide that to +10 by 4, which gives us a +2.5. So each sulfur is effectively losing half an electron, or half a mole of electrons, really, we should say. And the quicker way, I guess, is just to look at the charges. And you can see on this side here, we've got the -2, but we've got a 2 here, so that becomes a -4. And on this side, we've only got a -2. So you can see I've added an extra 2 electrons on that side. So 2 different ways of looking at oxidation numbers. That's the iodide one. Okay, and again, you can look at oxidation states. So we go from 0 oxidation state to a -1. And to do that, we're going to have to actually add electrons onto this side. Okay, you see the 2 electrons there. So hopefully you could recognize this as being therefore a redox reaction. And that's the overall equation there. And also, why is it there then? Why do we have that reaction? Well, the reason is because we only need to produce a very, very, very small amount of iodine to produce that blue-black colour. We put a little bit of thiosulfate in there to react with any iodine that initially forms, so that that blue-black colour doesn't appear instantly. Yeah, so that's the reason of thiosulfate. So it's not actually part of the iodine reaction of the hydrogen peroxide and iodide ions. It's there to just allow us actually being able to measure the rate. Okay, so you can see there I've kind of summarized that up. I say there are 2 reactions actually going on in the iodine clock reaction. This is the one we're actually studying, and this one here is just any iodine that is produced initially gets reacted, and so we don't get an instant blue-black change. You're only going to get that blue-black change once all this thiosulfate has been used up. So once all your fire is gone, then this reaction can start producing iodine, and we see that blue-black colour appear. Okay, so just very quickly then, I'll talk a bit of moles calculations. How much iodine would we have to actually produce in reaction 1 before we see the blue-black colour appear? Okay, so first of all, we've got these quantities. These are actually in your method that you'll see in your prac. So I'm going to ask you to work out the moles of sodium thiosulfate. Okay, so moles sodium thiosulfate. Okay, your concentration times by your volume. And you see here we've got 5 times 10 to the -5 moles. All right, the next thing then I'm going to ask you to do then is, therefore, on that basis, how many moles of iodine would we have to produce to use up all that thiosulfate? Moles of iodine. Just need to look at your stoichiometry. So we're looking at reaction 2. So you can see here it's 2.5 times 10 to the -5. Hopefully you can appreciate that it's a 2-to-1 ratio. Okay, 2-to-1 ratio. Right, so we know a little bit about the iodine clock now. We know it's a timed event to see that blue-black colour appear. And we also know why the thiosulfate's in there. And that's to make sure that we don't get that instant blue-black, that we're going to have to produce quite a little bit of iodine initially before we actually get the blue-black colour appear. So here's some results now for you, and you can see here this is a past paper question, and it's asked you to work out the mean time taken for the reaction to take place. So I'm just going to pause again and let you do that. And hopefully if you've worked out your average for this run at 0.2 mole per decimeter cubed, you've identified there is an anomalous result in that set of results. So hopefully you didn't include the 46 in the average. So that's something that would, perhaps catch you out. And you see here that our actual mean time taken is 35 seconds. And then we come down to the 0.4 mole, you can see it's one of probably the easiest averages you could ever work out. Okay, so it's 17 plus 18, 18 plus 17, and we get an average time here of 17.5 seconds. And I'm just going to talk to you very, very quickly about the recording the results here, because if you are using a stopwatch to record the time taken, you wouldn't quote to the 100th of a second. Typically, when we're recording results, especially for something like the iodine clock reaction, you're going to record to the nearest whole second. All right, so that would be a sensible degree of precision for this experiment. So you won't record, anything other than the nearest whole second. And then I do have a slight issue. I've got this straight from the MARC scheme. You can see the average of these results here is actually 17.5. Typically, and I've had discussed this with other teachers as well, really, I would have thought you would write down 18, because you record your average mean to the number of significant figures that the data you've used to work it out. But that value has actually come straight off the exam board, 17.5. So I think, if you were to record to one decimal place, they'd obviously forgive you for that. So once we've got our timed events, so this is the time it took for the blue-black colour to appear, just very quickly work out your rate of reaction. A little pause. Okay, and then you can see there we've got a rate at the two different concentrations. And all I've done is I've taken the time, divided it into 1. This is the mean time, and you can see here I've also written down the unit of rate. Okay, good. So what we're going to do next then is we're going to talk about the method, and a very important point to make about one of the things that's done in the method. Okay, you'll see right at the planning stage, you have to decide what volumes of water and peroxide that you're going to mix together, and you are advised that the total volume must not exceed 5 centimeters cubed. Okay, so you can see here, here's a results table that's been used to record our data, or to actually set up the experiments. Actually, not even recording the time taken this one. This is just to make up your solutions. So okay, so I want different concentrations of peroxide. So obviously, just what I'm going to do is add different amounts of peroxide into my volumetric, into my conical flask. Sorry, I said volumetric. Now, okay. What we also do is we add water. I'm just going to explain to you why we add some water into our conical as well as the peroxide, and the quantities that would be added. So just a little pause for you to think about what the quantities of water you would add to flask 1 to 5. And hopefully you've come up with the idea that you need a constant volume. Okay, so let's get a constant volume. You can see here we've had different amounts of water. And basically what we're doing is we're just making the total volume up to a total volume of 10, 20, 45, 50 mil. So all of these come out as 50 mil, 10, 20, 45, 48, 50 mil. Why do we want a constant volume? Well, a constant volume allows you to come up with the assumption that if you change any change in the volume you've done here, that change in the volume is going to be proportional to what the change is in the concentration of the peroxide. So, for example, I know that this flask 4 is double the concentration of flask 5. Flask 2 is double the concentration of flask 4. Flask 1 is 5 times concentration of flask 1 is 5 times concentration of flask 5, and so on. If you didn't have that constant volume, you would not be able to do that, and that would make your using the results much more difficult. Okay, so what are the concentrations of the peroxide then? So we'll just do a quick calculation then. So let's work out the concentration of the peroxide if you have 1 centimeter cubed in the conical. Okay, so remember we've got a constant volume here of 50 centimeters cubed, and in the method it tells us we're using 0.1 molar solution. Okay, so if you work out your concentration form, your concentration of the peroxide. Okay, so you can see the first thing I've done here, I've worked out how many moles of peroxide I've got, 1 being the volume, okay, and 0.1 being the concentration. And then what I'm going to do is work out my concentration by dividing by the constant volume. You see here we've got 2 times 10 to the minus 3 moles of peroxide. Okay, so there's my with 1 mil. So what's the concentration now at 2 mil? Well, we don't need to do the calculation again. We don't need to do 2 divided by 1,000, blah, 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 because we've used a constant volume. We can now say, right, the concentration of the 2 mil is 4 times 10 to the minus 3. The 3 mil obviously would be 6, 8, 1 times 10 to the minus 2. Okay, so these are all now relative in terms of concentration to the 1 mil. So that's the reason we have a constant volume in this reaction. Okay, so here's a set of results. So what I'm going to ask you to do, I'm going to just give a very, very quick pause. And while you're pausing, I want you to plot, oh, sorry, not plot yet. Can you work out your rates of reaction, please, at these different volumes or concentrations of the peroxide? So I'm going to pause. Okay, and now I'm just going to show you the rate. So you can see your rates there. So the next thing we're going to do then is obviously draw a graph. Okay, so I'm going to let you now, and I should have said this at the start, grab some graph paper and plot those results for me. Obviously, you're going to have the concentration on your x-axis. That's your independent variable. That's what you are changing. And then you've got your rate, your dependent variable on your y-axis. Okay, so plot those two sets of results. And when you've done that, hopefully you get a graph that looks a little bit like this. Now, you can see here, I've actually plotted volume of peroxide. Equally, and you'll see this in a minute, I could have plotted that as concentration of peroxide. You know, that constant volume allows me to do that. And you can see I've plotted my results. And I'm just going to point out on my y-axis, you can see here the way I've plotted it, as I said, rate times 10 to the minus 2. And I've also obviously put my units there. So make sure when you are, you know, plotting a graph that you label your axes. If you've got standard form, just quote what the standard form is and make sure, please, that you do put your units, as I've done here, mil and s to the minus 1 for the rate. So what does this graph show us then? What do we now know about peroxide? Well, it shows us that rate is proportional to concentration. What does that mean? Well, hopefully you know what that means. If I double my concentration, what I am doing is I'm doubling my rate. We can see that by this straight line that intersects through the origin here. Okay, so it's actually directly proportional, and hopefully you are aware of, you know, what the change in concentration reactant means in on rate and what that means in terms of its order. So we see here, obviously this peroxide is not zero order. Changing its concentration is changing the rate. If it was zero order, what you'd actually see is just literally a horizontal line going across there. You change your peroxide concentration and the rate stays at, let's say, 2 times 10 to the minus 2 s to the minus 1. Okay, that would be your zero order. We can see is actually is first order. It is directly proportional. And if you have a quick look on the graph there, you can see that was an easy one to see. If we go to the perhaps the 2 mil, so you can see there we've got a rate of 1.5 times 10 to the minus 2. We go to 4 mil and we see it's approximately double at 3 times 10 to the minus 2. Okay, so what's our rate law? Well, we can't write all the rate law, but we can write some of our rate law. Obviously, we've got our K, which is our rate constant, and we now know that the peroxide is first order. Okay, what we don't know is about the other reactants. We don't know anything about the protons, and we don't know anything about the iodines. So we're going to have to do some more work on those. Okay. So yeah, we don't know what the order of H plus. You see here it's volume H2SO4, but really it's the H plus ions. We don't know the order with the respect to the iodide ions. Remember the fire sulfate here is nothing to do with the actual reaction as such. Okay, so yeah, we're going to look at how we can work out the order of the iodide and H plus. And there's various things we can do. Now I'll just show you here. As I said earlier, I'm a bit lazy. I plotted the volume. I could have quite have easily just plotted the concentration. Instead of writing 1 mil, I could have written 2 times 10 to minus 3 moles per decimeter cubed. Okay, graph comes out exactly the same, so no issues there. Okay, so let's look now then at how we could establish the order of the iodide and the H plus. I'm just going to go back a little bit there. Bear with me a second. Okay, so how would I establish these orders? Well, the one thing I could do is I could do a very similar experiment. However, this time I'd have a constant volume of peroxide, and then I would just change the volume of the iodide ions. Okay, and I'd have a look then at what effect that would have on the rate, and then same with the H plus. I'd have a constant volume, but I would be changing the volume of H plus ions being added or changing the concentrations as such. But we're not going to do that for establishing our rate orders with respect to those species, because I want you to kind of be aware of reaction mechanisms and what a rate law tells us about a reaction mechanism and what a mechanism tells us about a rate law and so on. Okay, so here's a quick question for you. I'm just going to suggest you pause and have a quick read of what's written there. So we have a proposed mechanism, and we can actually use this proposed mechanism to, well, suggest what the orders of the other species are, the H plus and iodide ions. Okay, so let's look at the mechanism now. I've just zoomed in here on the mechanism, and hopefully you know the kind of like how a mechanism relates to rate law. Any species that is in or before the rate determining step would be in the rate law. Any species that's not in the rate determining step or comes after the rate determining step is not in the rate law. Okay, so let's look at then the mechanism, and we see here we already know the peroxide is first order, but we can see here step one's the slowest step of our reaction. Okay, so what does that tell us then? Well, it confirms to us that H2O2 is first order. You can only see one molecule of it. Okay, and this is the first step, so there's no other molecules in previous steps. What else does it show us then? Okay, well, it shows us that the iodide ion is also in that slow step. Okay, so what that tells me then is that the iodide is also first order. And I just want to point something out to you. If you look at the balanced equation, okay, you can see actually it says that, well, there's actually 2 moles of iodide ions involved in this reaction. So where's the other iodide ion? Why is it not in the rate law? Well, if you look in the equation in step 3, we can see the other iodide ion here, but it's not included in our rate law because it comes after the rate determining step. Okay, just to point out, by the way, if it was in the rate determining step, let's say step 3 was the rate determining step, then all species would be included. We'd have H2O2 would be first order. The iodide ion would actually be second order because we've got 2 molecules in or before the rate determining step, one in step 1 and one in step 3. So that would actually make the iodide second order. And step 3 was the fastest step. The H plus would also be in the rate determining step. In fact, the H plus, looking at it, would also be second order because we've got one in step 2 and one in step 3. But as we've said, or as the mechanism proposes, step 1 is the rate determining step, and hence the hydrogen peroxide is first order, the iodide is first order, and the H plus is what we call 0 order. Okay, wait a second. And you can see here the way the mechanism I've written the rate law. You're probably aware, but typically, if something's first order, we don't put an indice value. If something's second order, we do state that it's second order with a 2. And if something's zero order, we tend not to actually include it in the rate law. Let's go back. So typically, that wouldn't actually be included. You just literally would write H2O2 and times the concentration of iodide minus. Oh, and just a little mistake. I hope you can all spot my mistake in my rate law. That was me deleting something earlier and then forgetting to put it back in. Yeah, what's missing? Yeah, hopefully you've said K. Okay, don't forget your rate constant. They're kind of important in rate laws. Okay, so we've used the mechanism there to help us establish what the order with respect to iodines would be and the order with respect to the H+ ions, which are also reactants in that reaction, the iodine clock. Now, what we're going to do next then is the actual question that we're being asked to do here, and that's to write a balanced equation, okay, for the reaction based on the mechanism. Now, the advice I always give to my students when we do this in class is, look, these are tricky and they're something that you would leave to the end of the exam. They're not something that you would kind of invest much time in during the exam, because they're gonna involve you doing a lot of thinking. Okay, so these are the sort of questions where you go, okay, that's something to come back to if I've got time. So we've got to the end of the exam. We're kind of going around now trying to pick up some more marks. Okay, so let's have a look how we do this. Actually not that bad, to be honest. The first thing we've got to do is we've got to look for our intermediates in this mechanism. Now, what do I mean by an intermediate? Well, by intermediate, I mean something that's being formed in one of the steps, but then in a subsequent step, it actually gets consumed. Okay, so I'm going to ask you to have a quick look, first of all, for one intermediate. And hopefully you've spotted straight away that one of our intermediates is this species here. Okay, so you can see in step 1 we've got this O- being produced, but in step 2 it's immediately consumed. So that indicates to me that it's an intermediate. Okay, can you see another intermediate then based on that? Okay, so hopefully we've spotted that this species is also an intermediate. It's formed in step 2, but it's then being consumed in step 3. Okay, so these intermediates then, they don't actually become part of our stoichiometric equation. Okay, so what we would do is we would kind of just ignore them. So you can see I've done that by obliterating them, getting rid of them. Right, there's no catalyst here. I've got another one where I'll show you a catalyst in a minute, so you'll be able to spot those if they are present. So then what we're going to do now is we're just going to look at our reactants and the products. Okay, so let's look for our reactants. That's anything that's going to be on the left-hand side of the arrow. So we've got this species, this species, this species, that species, and that species. Okay, there we go. So you can see I've kind of broken it down about as much as you can break something down. And then we'll do the products as well. Okay, so one of our products is this, H2O. And we've also got another product here, another H2O actually. There's one H2O there and one there in this step being formed. And then we've also got the I2 being formed as well. Okay, so there's our products. Okay, so what I'm going to do now is just summarize that into the balanced equation. Here's our reaction. Okay, so we got H2O2, 2I2 minus, one there and one there, and 2H plus. 2H plus, and then product, we've got 2 H2Os and we've got the I2 as well. And if you go back to the reaction, you can see that's exactly as it should be. So yeah, you know what have we done there then? We've looked at a mechanism and we've used that mechanism initially to establish the order of some reactants. We've also used that mechanism to be able to write a balanced equation, and in doing so we've discussed this concept of intermediates. Okay, so let's move on now to another question. Okay, just what I'd practice this one with you. I have done a thing on rate before. It was beyond the previous Carlin videos. This is using initial rate data to establish the order of a reactant. Okay. So, well, I'll just do a quick pause, and you could use the initial rate data there to write the rate law, i.e. To establish the order of the A and B. So let's start that then. Okay, so we can start with looking at the order with respect to A. So what we're going to do then is we're going to change the concentration of A and see what impact that has on our rate of reaction. And the obvious thing to do to look at is experiment 1 and 2 if we wish to establish what's happening to the rate we change concentration of A. And the reason I'm picking that one there is you can see that the concentration of B is unchanged in experiment 1 and 2. And I guess when you're using initial rate data, that's one of the things you want to look for, is a reaction where something stayed the same, they've changed the other reactant. So what they've done to the concentration of A and B, well, concentration of A and what's happened to the rate. So if we have a quick look, okay, so the change in concentration of A, you see there, all I've done is I've taken the higher concentration divided by the lower concentration to see what the change in the concentration is. So it's basically the concentration of the experiment 2 is 1.5 times greater. And then what we do is we look at what effect that's had on the rate. So again, what we do there is we simply take the fast rate and divide by the slow rate. And you can see here, the rate is 1.5 times greater. So hopefully now you know what the order with respect to A is. Okay, you double basically it's proportional. So it should be first order. Okay, then we're going to look at B. So we now know A is first order. That may come in to help us a bit later, but let's look at then working out the order with respect to B. So on B, you can see in experiment 2 and 3, A is being kept the same. So what they've done to the concentration of B. Okay, so I'm going to take the fast rate and divide by, low concentration divided by the, high concentration divided by the low concentration. So you see it's 2.5 times greater. Okay, so experiment 3 is 2.5 times greater. Now, what's happened to the rate? Well, it's had a massive impact on the rate, and I could tell you instantly, okay, this is going to be second order. And basically, the change in concentration is, change in rate is the same as the rate squared, okay? So let's have a quick look there. So effect on rate, so I'm going to take the fast rate divided by the slow rate, and you can see it's 6.25 times greater. And so, I mean, as you can see, if it was first order, you'd expect the rate to just be 2.5 times greater. But if we have a look at the effect on the rate, okay, so we'll take the fast rate. Okay, well, you can see here, I recognize this was the square root of 6.25 is 2.5. So basically, 6.25 is 2.5 squared. So I now know that B, wait a second, let's see my buttons, B is second order. Okay, so the change in rate is the same as the change in concentration squared. Great. Mechanism, then, does that mechanism fit? Well, possibly. We've got A plus B goes to intermediate, and then intermediate plus B goes to product. Okay, well, yeah, that could potentially work. It just depends what our rate determining step would be. Okay, so I'm going to suggest step 1 or step 2. I'm going to let you have a little think about whether it's step 1 or step 2. A little pause. And it is actually step 2 is the rate determining step. I just want you to see why step 2 would be our rate determining step. Let's give you a little moment to think about that. Okay, so the reason I'm saying step 2 is a slow step is because we found that B is second order. Well, that means there must be 2 molecules of B, not that B is a molecule, but 2 molecules of B in or before the rate determining step. Okay, if step 1 was my rate determining step, the order of B would only be first order. We can see here order of B is second order, so that means that there must be 2 molecules involved in or before. So we've got 1 here and 1 here. So that would fit with our rate law. Okay, so here's another quick one for you to do. The following mechanism being proposed for the reaction of trichloromethane and chlorine. Okay, so the first thing I want us to do is to write out a balanced equation for this reaction. Now, there is something here, we did mention it earlier, there is a catalyst involved in this mechanism. So let's see if you can see what the catalyst is. Okay, well, before we do the catalyst, let's look for intermediates. Okay, I'm just going to go back, hopefully you can see that. So have a quick pause, look at it for your intermediates, something that's been produced but then being consumed. And I did show very quickly, unfortunately. You can see there, it's these chlorine atoms. Okay, I guess these would be free radicals, right? Unpaired electrons. Okay, so you've had homolytic bond fission of that diatomic chlorine. So why are they intermediates? Well, we're producing them in step 1, but then one's consumed in step 2 and the other's consumed in step 3. So we'll include those in our balanced equation. Okay. And then obviously we've got the CCl3 as well. Okay, so you can see CCl3 is being produced in step 2, but then it's consumed in step 3. So if we got rid of all our intermediates, added up all our reactants on the left and all our products on the right, you should come up with the balanced equation there. All right, so I've identified my intermediates, things that are produced but then consumed, produced, consumed. Okay, and that gives me my balanced equation. And then I'm going to write down our rate law. So this is where we come into the idea of our rate law being Cl2 plus CHCl3. Okay, so why CH2 and why Cl2? Well, we can see here, here's our slow step. Okay, and we see that we've got CHCl3 is involved in the slow step, and we have a Cl2 involved before the slow step. Okay, there we go. So this is the one with the catalyst. I thought it was that one that had the catalyst in, but it's actually this one with the catalyst, and we'll talk about what catalyst is in a minute. Let's look at our overall reaction then. Okay, so again, we start off by getting rid of our intermediates. So a little pause while you look for your intermediate, something that's been produced and then consumed in a subsequent step. Okay, and hopefully you've recognized that that's an intermediate. Okay, right, any other intermediates that we can see there? I'm just going to have a quick look. No, but no. We're going to talk about this species. Okay, just tell me what's happening with this species then. Okay, you can see it there and you can see it there. Okay, this is a catalyst. And the reason it's a catalyst, you can see that in step 1, it's being consumed. Okay, so that would look like a reactant, something that's being consumed. Okay, but then you can see in step 2, it's been reformed. Okay, and this is why catalysts don't get consumed in reactions. They get consumed, but then they can be regenerated. All right, so this is a chlorine-free radical, and you can see here this chlorine-free radical is a catalyst. Anything that you consume in a step, but then produce again in a subsequent step, if it's left over at the end of the reaction, you have a catalyst. Okay, overall equation then. There's our overall equation. I've not included the catalyst in there. Remember, catalysts don't get consumed. Okay, so we've got the O3. We've also got the O- as reactants, and then we've got the products O2 and O2, so 2O2. So what about the Cl dot, sorry, not Cl minus, chloride ion, it's a chlorine-free radical. Where does that go? Well, like any good old catalyst, it's going to go above the arrow. Okay, so I hope you can get the idea what a catalyst is. Something that gets consumed but then regenerated, so technically not used up and not produced. The rate law then. Okay, how do we write the rate law for this? Well, there's our rate law, and catalysts, yeah, they must be in the rate law, and you can actually see here a good way of spotting whether something's a catalyst is if you look at the rate law. Okay, and you don't see it as a reactant in the actual balanced equation. Let's say the chlorine-free radical wasn't being shown above the arrow, you would see that rate law and go, well, I can't see a chlorine-free radical in that overall equation. Right, the chlorine-free radical must be a catalyst. Okay. So just very quickly then, going a little bit longer on this one. Quick question for you to have a quick go there then. We've got a rate equation for the decomposition of N2O5, dinitrogen pentoxide, to form oxygen and nitrogen dioxide. And it's telling you here that the overall order of this reaction is first order. So that's the total order of the reaction. So the first thing I'm going to do here, it says write the rate equation for the reaction. So before I do that, I just thought I'd put the balanced equation for the N2O5 breaking down to form its products. That's the balanced equation there. And the rate equation, well, it tells me that the N2O5 is that the reaction's first order overall. There's only one reactant here, it's decomposition, it's N2O5. Okay, so what I know then is rate is equal to K N2O5, with the N2O5 here being shown as first order. And it says just a rate determining step for this reaction. Right, these are the really tricky ones. So I'm just going to give you a little bit of advice here. If you're in an exam and you're asked to write a rate determining step or anything like a mechanism, as I said earlier, don't do it to the end. Okay, but we're going to be okay. This will be all right, because I'm going to give you a little tip. Write a rate determining step for this reaction. We know the N2O5 is first order, so we know it must be in or before the rate determining step. Okay. So that's what I'm going to suggest as my rate determining step. You can see here I've got one molecule of N2O5, and then on the right hand side, all I'm going to suggest you do, and it can be absolute nonsense what you write down here. What I've written down isn't actually nonsense. I kind of had a little think about it, but as long as what you write on the right hand side is stoichiometrically correct to the left hand side, then you're on a winner. So you've got to show that the N2O5, there's only one molecule of it in the rate determining step. You don't want to put a 2 in there, that would ruin everything. And then this side here just basically has to add up to the left-hand side. So we've got 2 nitrogens, 1, 2, and we've got 5 oxygens. 1 plus 3 is 4, plus 1 is 5. So yeah, that would be a sensible rate determining step. I'm just going to run you through something that's not really asked for here, but why not? What's the next step in that mechanism? Then what would be sensible? Well, I'm going to give this a subsequent step. A suggestion is this. Now, the reason I've done that is I want you to think about, well, would that actually work? And what do I mean, would it work? Well, really, if this is my mechanism, the mechanism should reflect the overall stoichiometric equation. So let's have a quick look. Hopefully recognize some intermediates here. So I'm going to just get you to think, does that work? Does that kind of add up to what we know the balanced equation is? Okay, and oh, bear me a second. And yes, it does. Okay, so if you have a look there, this isn't an intermediate, it's something that gets consumed. Okay, and it's certainly not, let me a second, certainly not a catalyst. So yeah, that would kind of work overall. Okay. Right. So a little bit longer than normal. So that's the end of my session. We've got session 4 next. That's with Ms. Stevens, and she'll be looking at the approach to Unit 5 assessment, which I've covered quite a lot with you anyway in my session on entropy and Born-Haber cycles, and also on, sorry, that was on my accurate entropy change calculations. That's a year 12 one, and then on this session 3, the iodine clock mechanism. Okay, so thank you for listening, and I hope you found it useful, and remember, work your way through it and pause a lot. Thank you.